Okay, so let's try and find all asymptotes. So in this first example, a f of x is equal to 2x minus 5 over 3x squared plus 1. And the vertical asymptotes, they'll be found if the denominator is equal to 0. So 3x squared plus 1 would have to be equal to 0. When I subtract 1 and divide by 3 and take the square root, I'll be taking the square root of a negative. So there are no vertical asymptotes. When I move on to horizontal asymptotes, then I look at the degree. So the degrees of the top is 1, and the degree of the bottom is 2. And remember, that's m, that's n, and m in this case is less than n. If m is less than n, then I have a horizontal asymptote at y equals 0. Example 2, if I have a function where I have, say, 2x plus 1, and on the bottom 3x minus 1, then the vertical asymptote is what occurs when the bottom is equal to 0, so 3x is equal to 1, or x is equal to 1/3. There's your vertical asymptote. So when graphing, if that's 1 at 1/3, there's some sort of asymptote, an asymptotic behavior to our graph. And the horizontal asymptote occurs, well, this is degree 1, this is degree 1, there's m, there's n. In this case, m and n are the same. When m and n are the same, then you use the coefficients to those two things, and you get y equals 2/3. So this is 1, this is about 2/3 here. So the behavior for the asymptotes is really just the end behavior. So by end, again, I mean what's happening at positive infinity for the x values and what's happening at negative infinity for the x values. So that gives you some idea of what the graph may look like. It won't, fill in everything. You're going to need to still use the table of values and get some other values on there. But it definitely gives you some tendencies to what the overall behavior of the graph can look like. Third example, if I have f of x is equal to 4x squared minus 3, there's your polynomial function on the numerator, polynomial function on the denominator. Let's do vertical first, like I've done before. The vertical asymptote is when the denominator equals 0, so not too difficult to solve this. So I have a vertical asymptote at -1/2, and the horizontal asymptote, well, now I look at these degrees and I notice that m is bigger than n, so there actually won't be a horizontal one, but there will be either a slant or oblique one, and the way that I calculate that is with long division. So I take 4x squared minus no x's minus 3, that's the numerator, I divide it by the denominator, and I look to see how many times does 2x go in. It goes in 2x times, so there's 4x squared plus 2x. That's what I subtract. I get no x squared. I don't even need to write that down. And I get minus 0 minus 2, so I have -2x, and bring down this one. That goes in -1 time. And I don't actually need to do any more work because this equaling y will be my slant asymptote. And if you want to see what that will look like, take a look at graphing this on your graphing calculator and graphing this on your graphing calculator, and you should see on your graph 2x minus 1 has a slope of 2, so it looks something like this, and it's an asymptote, so I'll make it a dotted line. And your graph should approach this somehow, and it's actually quite neat to see. So go ahead and do that on the graphing calculator. When you get to this step and you've finished this numerator, you have no more terms to divide in. That's when you can just make it equal to y. We don't really care about any remainders, and that's how you can find any kind of slant or oblique asymptotes. Okay, let's take a look at a couple more things. X and y intercepts, how do we go about calculating those? Because they're really useful and actually quite easy to graph and calculate. So x and y intercepts. To find x intercepts, all you do is make y equal to 0 and solve. And to find y intercepts, you make x equal to 0 and solve for y. This is probably easiest to see through an example. So Okay, so let's take a look at an example. F of x is equal to 2x minus 6 over x minus 1. So to find the x-intercepts, we make y equal to 0. Making y equal to 0 is the same as the f of x, so 0 equals 2x minus 6 over x minus 1. And essentially all we have to do is solve when is this numerator equal to 0, because 0 divided by anything is equal to 0. So when is 2x minus 6 equal to 0? Well, when x is equal to 3. So that tells us on our sketch that when x is equal to 3, we have the x-intercept. To find the y-intercept, we make x is equal to 0. So f of x is equal to, now just substitute in 0 anytime you have an x, and so you get 2 times 0, which is 0, take away 6, over negative 1, which is 6. And so you get the y-intercept of 6. And you know 2 more points on your graph. So when you start combining this together with, oh, there is a vertical asymptote at x is equal to 1, and there is a horizontal asymptote at x is equal to 2, you start to get an idea of what the graph might look like without actually having to grab your graphing calculator, which you can do. You can go ahead and check and see if the graph actually somewhat matches the end behavior of these asymptotes and the asymptotic behavior around x is equal to 1. And one last section for us to look at. I mentioned earlier that sometimes, most of the time you get asymptotes, but sometimes it's only possible asymptotes. And the reason that it's only possible is if you have a function like f of x is equal to x minus 1 over x squared minus x, and you start to think about, well, where are these vertical asymptotes? Well, you might start to think, well, there's a vertical asymptote. Let me just do a little bit of factoring here. If I take out this, there's a vertical asymptote at x is equal to 0, and there's another one when x is equal to 1, and I'm getting those from when is the denominator equal to 0. However, those are just the possible vertical asymptotes, and the reason that they're possible is, well, when you take a look at the graph of this one, if you were to take a graphing calculator and actually graph this, the graph would only have one asymptote, and that asymptote would be right here at x is equal to 0 as a vertical one. There is a horizontal one, and you can use the rule that if the bottom is bigger than the top, then there's a horizontal asymptote at y equals 0. But we're just dealing with this vertical asymptote, and there isn't an asymptote at x is equal to 1. But if you use the table feature on the graphing calculator, you'll see that this point right here actually doesn't exist. And that's because there is a restriction. X cannot be equal to 0. That was an asymptote. And x actually can't be equal to 1 either. And what that creates is a hole in the graph. And the location of the hole is quite easy to find if you factor and if you notice that these are common factors. And you just end up with the graph of 1 over x. And this blue line essentially looks like 1 over x with this little tiny hole in it, and the hole's got an x-coordinate of 1, and the y-coordinate you can find by just plugging in a 1 into your simplified equation, so 1 over 1 is 1. This hole is actually at the coordinate 1, 1. And it's actually known as a hole. It's also known as what's called a discontinuity in calculus. And if you're taking calculus concurrently, or if you take calculus in the future, this is a neat little thing that we look at when we're doing graph sketching, as well as revisiting asymptotes and x and y intercepts as well. This is actually a fairly significant preview of graph sketching for calculus as well. That's it for today. We'll see you in class.